talking about percentages, and remember, any kind of percentage is just the part you're interested in divided by the whole, the total, times 100. And we saw 3 different ways of doing a percentage. You could do it where both the part and the whole were in mass, where the part and the whole were both in volume, or where the part, the solute, was in mass, but the whole, the solution, was in volume. So we saw different variations. So here's one. It says what volume of a 10.0% V/V, so volume over volume, formic acid solution contains 2.0 milliliters of formic acid. So let's just read that again. What volume of solution? So once the volume of the total solution, it tells you it's a 10% solution. So out of that total solution, so what would the total solution be if you had 2 milliliters of just the solute, just the piece you're interested in? So let's make a few notes here. So we're trying to find volume of solution, right? The whole solution, that's the whole solution. So 10%, 10.0%. Well, any percent is out of 100, right? So 10% means there's 10 out of every 100. So 10.0% means there's 10.0. Okay, well, in my case, what's my unit? Well, it's VV. So that means they're both in volume, right? So both could be milliliters, both could be liters. Well, they give me one in milliliters, so I'll just put mine in milliliters to make it easy. So let's say 10.0 milliliters of whatever you're looking at. What's the solute? What's the thing that's being dissolved? And in our case, it's this stuff, formic acid, it says. See that? So I'll just put acid just to make it shorter. Over what? 100. What's the unit on that one? Same thing. 100 milliliters, and that's the whole solution, right? The whole solution. So abbreviate solution. SOL apostrophe, and that's a common solution abbreviation. Okay, so that's my conversion factor between milliliters of solute, the acid, and milliliters of the solution, the whole thing. So I'm starting with 2.0 milliliters of the acid. Well, I need to use that as my conversion factor, the percent. Well, in order for acid to cancel, I'm just going to take this and just flip it and put it in here, right? And then the acid will cancel, and I'll be left with milliliters of solution, which is what I want, volume of solution. So it works perfect. So let's put the 10.0 down here. The 100 ml solution up here. And what is that? 200 over 10, about 20. It's like 2 sig figs, yeah. So 20 milliliters of solution. Okay, well, hopefully that's a little refresher if you've been practicing that some. Okay, I'm going to skip this one. So now another way we can measure concentration. It's still solute over solution, but now it's not masses, now it's not in volumes, now it's in our old friend, the mole. This is called molarity. So molarity is moles of solute over the liters of solution. So this is very handy for us in the laboratory because we like to use solutions, and it's even easier if they're already converted into moles for us so we can do our relationships between reactants and products instead. So molarity has a symbol of a capital M. Now when you see it written oftentimes in your textbook or things like that, you notice the capital M is either bold or it's written like italics. It's hard to write on your paper though, things like a capital M in italics. So normally the way it's written for us is just put a line under it. We just put like capital M with a line. That means molarity. Versus capital M without a line is normally like mega. Right. So yeah. So you've already seen this actually being used in the lab, probably. So you'd be in the lab someday and you'd be using like a reagent on chemical off the cart and it'll say 6M HCl or 1M HCl. Well, that M was this. moles per liter. It was the concentration. It's how many moles are in every liter of that solution. Okay. Uh-oh. What's going on here? There it goes finally. Okay. So let me just do a quick example. We'll solve for molarity. It says, what is the molarity? If you have a solution and you put 3.29 moles of sodium nitrate into 765 milliliters of solution. So, well, molarity is moles of solute over liters of solution. So we need moles of solute and we need liters of solution. Well, we are partway there because we have the moles of the solute given to us, right? It's 3.29 moles. And what's the formula for sodium nitrate, remember? NaNO3, right, good. And we want it to be over liters of solution, but we have milliliters, so we just convert milliliters into liters, right? So 765 milliliters. I guess I'll just do it down here separate. Just work it out for you. Milli is 10 to the negative third liter, so 0.765 liter. So 0.765 liter. There you go. So multiply that out in your calculator. What'd you get? 4.95. 4.95? Anybody else? 4 point. Sorry, I'm hearing 4.3. I'm hearing 4.95. I'm hearing 4 point something. So how many sig figs should I have? So what is it? Okay, and I'm going to write capital M with a line. That means molarity. So the way you pronounce that, by the way, is you would say, oh, it's a 4.30 molar solution. Molar, like the big teeth in the back of your mouth, your molars, like that, molar. So the molarity is 4.30, or the molar concentration is 4.30. That's that. Okay, so that means out of every liter, you had 4.30 moles. Okay, let's try another one. What is the molar concentration? Again, molarity, same thing, of a solution that has a volume of 6.5 liters and it contains 660 grams of calcium phosphate. So we need the moles on top and the liters on the bottom. The liters we have, we don't have moles, we have the mass. How do we turn that mass into moles? Molar mass. Well, you can only do the molar mass, though, if you have some naming skills and you can figure out what the formula of calcium phosphate is. So hit me with some knowledge here. What's calcium phosphate? Wow me. Ca what? 3. There we go. Right. So you have to take 660 grams and turn it into moles. So add up your calciums, your phosphorus, your oxygens. Pull out your periodic table if you haven't yet. Oops. Calciums are about 40, so that's 120. 31 and 62 and what is it? 64 and 128. 62 is 100. 62 and what did I say? 128. 190. 310 something. That sounds good. Man, maybe work for that. 310. Okay, that's the mass of a mole of calcium phosphate. Good. So it's going to be, I don't know, 2-ish moles. What is it? 3 sig figs? 2.13 moles. Okay, so now for the molarity, I just take the moles, 2.13 moles. divided by the liters, 2.5 liters. It's going to be something a little less than 1, so what is it? How much? What is it? 0.851. How many sig figs? Try again.
2.
How many sig figs are in the volume? Just 2. 0.85 molar. Capital M with a line. Molar. Okay, well, let's try one slightly different here. So let's say you want to make 6.7 liters of a 1.2 molar solution. And you're using copper 2 fluoride. So you're in the lab, and I hand you a bottle of some lovely copper 2 fluoride, and I say, go to work. Make me 6.7 liters, and I want it to be 1.2 molar. So you have the liters, you have the moles per liter. So you could find the what? The moles, but you ultimately want the grams, the mass. So once you have the moles, you can turn the moles into mass. With our old friend, molar mass, right? So try that out, think about it, help each other out. I'm happy to help you out too if you have a question. Sure you know the formula for copper 2 fluoride. Maybe we'll discuss that with your neighbor eventually here. So, what's the formula for copper 2 fluoride? CuF2. Because copper is 2 plus. Fluoride, well, fluorine's 1 away, so each one of those is 1 minus, so you need 2 of them, so CuF2. Okay, we'll compare with somebody if you haven't yet. Talk it over. What you think? How many grams would you have to use to make 6.7 liters of 1.2 molarity? Okay, let's work it out here. What is, so let me just break it down here again. 1.2 molar, that's the same as saying 1.2 moles per liter, right? That's what that means. And it's moles of what? You said it was moles of CuF2, not Cu2F, because copper 2 means copper is 2 plus. Again, fluoride is 1, so I need 2 fluorides to balance out the 1 copper. Okay, so I can use that as a conversion from moles to liters. So take my 6.7 liters times 1.2 moles per liter. Now I have moles, but I want mass. So you add up a copper, 2 fluorines, 38 and 63, wasn't 100. Yeah. So what was that? 101.55, okay. There you go. So it looks like 2 sig figs, so what'd you get? 820. 2 sig figs. Or 8.2 times 10 to the second. 2 sig figs. Either way is fine. 816 is 3 sig figs. So make it 2 sig figs. Okay, let's try one more. How many liters of 0.10 molar aqueous solution of NaOH could you make if you had 10.0 grams of sodium hydroxide? So you have 10 grams lying around, and you need to make a 0.1 molar solution. Well, how much 0.1 molar could you make if you only had 10 grams? So think about that one. Talk it over. Just think about what we know. So I know the mass. I know the moles per liter. I want the liters. So the moles per liter is going to be a conversion. It has 2 units in it. The molarity, moles per liter. So I'm going to start with the one that's not 2 units, the 10 grams. NaOH. So, what am I going to do first with the mass? Molar mass. So it's about 40-ish, right? I think it's actually exactly 40, I think. That's the mass of a mole of NaOH. Well, this tells me 0.100 moles per liter, right? That's what that molarity means, moles per liter. Well, I want the moles to cancel, so I'm going to put the mole part on the bottom and the liter part on the top. So 0.100 moles per liter, right? Moles of what? Moles of NaOH. All right, so that was the molarity. There you go. And yeah, it's about a fourth. So 0.25. Yeah. So what do you say? 22.5. Makes sense. Looks like 3 sig figs. So 2.50. Yes. Sorry, I got paused there. Okay. Dilution. Here's an important little topic. I'll tell you why in a second. But dilution is where you have a solution of something and it's really concentrated. It's far too concentrated to eat or use or to give to a patient or whatever it is, let's say. So you have to dilute it. You have to make it less concentrated. So let's say you have, I don't know, a simple example. Let's say you have a coffee. It's just way too strong, way too concentrated. Well, you dilute it. So you pour in a little bit of extra water or something. Or you have some salt water. It's just way too salty. So you pour in some extra salt, but make it a little bit more dilute, quote unquote. Well, so when you think about that, Again, let's say it's strong coffee and you're making it more dilute. Well, you just add in more water. You haven't changed the moles, the amount of coffee. You just changed how much solvent there was in there, right? Right. So the volume just got bigger. Or it was really salty water, and you added in more water. So now so the volume has changed, but still the same amount, the same moles of salt, right? You haven't changed that. You're not actually making it less salty by actually reaching inside and taking out the salt. You're adding in more solvent. So there's a handy formula we can use then. You can use it that'll relate the concentration of the volume of the really concentrated stuff to the concentration of the volume of the more dilute stuff we're making. And we just use this little formula. C1 V1 equals C2 V2. C is concentration, V is volume. The other way that you'll see it, which is the way that I always learned it, but your book uses C for some reason, I learned it M1 V1 equals M2 V2, but same thing. Just molarity times volume to begin with equals molarity times volume afterwards. But it technically doesn't have to be molarity. Concentration could be even, it could be molarity, but it could be something called molality. It could even actually be like your percentages, any kind of concentration. So I'll just show you how this works here. So let's say you have a really concentrated 12 molar solution. So that's really strong. There's a whole lot of KCl in that. And you want to dilute it and turn the 12 molar into only 1.5 molar. So you're trying to make 5 liters of 1.5 molar. So how much of the really strong stuff would you have to dilute to bring it from 12 down to 1.5? So again, it's real easy with our handy little formula here. So M1 V1 equals M2 V2, or again, C1, whatever you want to call it. So our initial concentration was 12 molar. We're turning that into 5 liters of 1.5 molar. So which variable am I missing?
V2.
No, I have V2 because I'm turning it into 5 liters. V1. So it's V1. So I want to know how much of the 12 molar do I need to use? So how much of the initial stuff do I need to use? So I'm going to solve for V1. So V1 will become M2 V2 over M1. So M2, well, that's the new molarity. The one I'm diluting it to is 1.50 molar. V2, how much is 1.50 molar? 5.00 liters of it. And starting with the initial molar, 12.0 molar. Okay, so molarity is going to cancel, it looks like. And you punch that in, and it gets 0.625 liters. I just know that just because it told me that. I have the picture. So, what is that saying? Well, that's saying, okay, so the way I would make 5 liters of 1.5 molar solution is I would measure out 0.625 liters of the 12 molar. So I would dump that into a flask. So I'd pour in 0.625 liters of the 12 molar, and then I would just add water, glug, 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 until I got to the total of 5 liters. Are you with me? So I would use 0.625 of the 12, and then add water until I got to the 5. And now the new concentration of that would be 1.5, because I've cut it in a sense, right? It was really strong, and I've cut it down from 12 to 1.5 by adding extra water. Does that kind of make sense? So I have my flask empty, and I would say, okay, so that tells me dump in 0.625, and then put in the rest, 4.375, whatever it is, right, liters of water. And then that new concentration is going to be 1.5, because I cut it down. Okay, yes, this is super important, like in all kinds of fields, especially like in medicine and such, because you'll often find that it's find that, for example, that it's much cheaper for you to ship very concentrated medicines, so you can, or solutions or chemicals or whatever, so you can just send fewer bottles of it. Does that make sense? You can send like could select let's see, so let's say then, for example, you could send out 10 bottles of a like 10 molar solution, or you could send out 100 bottles of 1 molar solution. So it's more cost efficient for you to send the really concentrated stuff, right, on a truck or whatever. And then when it gets there, then you have to dilute it down to whatever the amount you need, for the patient or the process, whatever it is you're using. So I actually heard a story from a friend of mine back at Fresno City. And she was the head of nursing at, I think it was St. Agnes Hospital. There in Fresno, and they came in one day. The who they call it? Okay, try again. I had a friend who was the head of nursing back at St. Agnes Hospital in Fresno, and one day the certification board came into the hospital, and did a spot check for all the nurses, and they made them all do a dilution right there. And they failed, and they fined the hospital $50,000, and all the nurses had to go back and be recertified because they couldn't do a dilution. So I'm saying dilution sometimes an important thing. And then I just read a horror story in the news. Well, not like recently, but like last year of a nurse who was administering like a nurse who was administering a medication then a medication then to like a mother who had just given birth. And she was supposed to take the medicine. The medicine they had then in the vial was to dilute it first and make it less concentrated. But she flipped her thing around and actually made it more concentrated and killed the mom right there on the table minutes after the baby had been born. So, again, dilution, sort of an important thing depending on your field and what you're doing here. So let's say what's the concentration of a solution prepared by taking 45 milliliters of 8.25 molar, and now you're diluting with water to 135 milliliters. So you've made it less concentrated, right? So you have the initial volume, the initial molarity, and you know the final volumes. You want to know, okay, what's the new less concentrated, the final molarity? So we're solving for which variable in that case? C2, yeah, C2, M2, C2, right. So we're going to, so if you want to use C, we'll use C. I'm flexible. So C2 is going to be equal to the initial concentration, the initial volume, over the final volume. So if we just want to label what we have here, here's my initial, whoops, no it's not, I lied. That's my initial volume, V1, right? 8.25, that's my initial concentration, right? And the 135.0, that's my new or my final concentration. Okay, so just plug it in here. So C1, 8.25 molar. How much of the 8.25 molar did I have? Oh, 45.0 milliliters, right? So those go together. 45.0 milliliters. And the total volume, 135.0 milliliters. Okay. So punch that all in, and what's the new concentration? It should go down because the volume went up. So 2.75? Okay, there you go. So that makes sense, right? Right? So it was this. And if you add water, you're making it less concentrated. So from 8.25 down to 2.75. Okay, let's try another one. You try this one. If you have 0.2 liters of really strong 15 molar, I mean, that's like melt your face off. You know, dissolve a body in that. 15 molar, and you want to cut it down to 3 molar. Well, what volume did it have to dilute it down to? From 0.2 liters to what? So figure that up, punch it in, talk it over. Okay, that sounds about right, because it's getting 5 times less concentrated, so it ought to be 5 times more of the volume. So 5 times smaller makes the volume 5 times bigger. So, to what volume? So we're trying to find V2. So V2 is going to be M1 V1 over M2, or you can use C. So the initial molarity was 15.0 molar. The initial amount of that was 0.200 liters. The new molarity, 3.00 molar. Yes, 1.00 liters. Okay, let's try a slightly little different variation here. So here's same kind of thing, but it says, how would you prepare 200.0 milliliters of 0.25 molar NaCl, starting with a 2.0 molar solution? So you're going to solve for the volume, but I want you to think about how would you actually prepare that solution? What would you actually do? If I handed you a bottle in the lab, and it was 2 molar, how would you turn that into 200 milliliters of 0.25 molar? Do the math first, and then think about, okay, how would I actually do that? Real quick, so, yeah. So the math you got, so I'm going to show you. I'm just going to draw a little picture here. Maybe it'll help. So you have a bottle here, and it says 2.0 molar. Oh, well, what do? Like I said, you would measure out of that into a flask or something. 25, right? Then you would add in water until you got to a total of 200, right? Are you with me? So you just add in water. So you basically would add in 175 milliliters of water, right? From 25 up to 200. So when you swirl it all up, you have now diluted it from 2 molar and turned it into 0.25 molar. With me? Kind of? Okay. Okay, good. Okay, well, now let's tie this in back to our old friend stoichiometry, using those balanced equations to relate one reactant to another or reactant to a product. So, we've done this a lot with, let's say, so many grams of reactant. Well, how many grams of product can you make? And using molar mass. And we even showed you then with gases. If you have volume of a gas, you can turn volume of a gas into moles using that thing, molar volume. But most reactions actually take place in the solution phase, not solids, not gases. Well, then for solutions, we have to use our new friend, molarity. So I'm going to draw a little lovely picture for you again. It's going to look familiar, but I'm going to add some pieces to it. So remember our friend, oops, go back to my green here, the mole. I showed you how to do a few things. I showed you how to turn particles into moles. And for that we used, what do you remember? Avogadro's number, right. Avogadro's number. Then I showed you how to turn moles into mass. And for that we know we use molar mass. Then I showed you the last chapter how to turn moles into volume of a gas, right? And that was using molar volume. Just a reminder that, remember, that's the same thing as 1 mole of any gas is 22.4 liters when you're at STP, right? So we've done all those. So we have solids, we have gases. Now with molarity, we can even do liquids. We can do everything. So we can use molarity. So I can also turn moles into volume, of a solution. And that's molarity. So just like molar mass was grams per mole, molarity is moles per liter. So that is our magical crossroads here through the moles. Everything goes through the moles. So you can now turn atoms into liters of solution. You can turn atoms into mass. You can turn mass into liters of gas. You can turn liters of gas into liters of solution. You can do anything you want now. It all just goes through moles has to be the crossroads. So first we started with this one, right? And I showed you this tool, Avogadro's number, and this tool, the molar mass. Then we added a third tool in your toolbox, the molar volume for gases. I have a fourth tool in our toolbox, the molarity. So it all just depends, what do you have? If you have a gas, use molar volume. If you got a mass, use molar mass. If you've got a solution, use molarity. So molarity, molar mass, molar volume. They all have molar in the name right there because they're all going to moles. Okay, everybody have that copied down if you want it? Okay, so let me show you one here. What volume in liters of 0.150 molar barium chloride solution is needed to react completely with 0.200 liters of 0.450 molar silver acetate solution according to this equation? So it's already balanced for you. So let's write in what we know. Always a good place to start. How many liters of barium chloride? So I'm going to put question mark, barium chloride, of 0.150 molar barium chloride. Do I need to react with 0.200 liters of 0.450 molar? So I have the silver acetate. How much barium chloride do I need to react with that silver acetate? Okay, so let's just forget about a second all these molarities and stuff. Let's say the question was, how many grams could I make from 0.200 grams? You would be all over that. You would say, oh, turn 0.200 grams into moles, mole to mole ratio, turn moles back into mass with molar mass. Same thing. But now it's not mass, it's liters. So now to turn liters into moles, we don't use molar mass, we use molarity. But it works the exact same way. So if it was mass, you use molar mass. If it's volume solution, you use molarity. But it works the exact same way. So it's just a little slight variation. So let's just start with what we know. I know 0.200 liters of silver acetate. That's a big, long formula. Oh, well, if I have volume of solution, only thing I can do is molarity of solution. Just like if I had mass, all I could do is molar mass. So I'm going to put in the molarity of that solution. 0.450 moles silver acetate per liter. Now I'm in moles of silver acetate, right? Well, how do I relate silver acetate over to barium chloride? Mole to mole ratio, right? So I look and I say, oh, for every 2 silver acetates, I need 1 mole of barium chloride, right? So we just plug it in, just like you would before. For every 2 moles of silver acetate, I need 1 mole of barium chloride. Now I'm in moles of barium chloride. Okay, well again I'll say, if the question would have said mass of barium chloride, you just said, oh, molar mass. But it's not, it's volume of solution. So moles to volume of solution, molarity. Are you kind of with me? So it's literally like the same thing, all you're just using is a slightly different tool. For masses, you use molar mass. For gases, you use molar volume. For solutions, you use molarity. So how am I going to put that molarity in? Well, I need the moles to cancel. So I'm going to put 0.150 moles on the bottom and then the liter on the top, so it will cancel. 0.150 moles barium chloride per liter. Okay? So that is that molarity, right? That is that molarity. And we cancel. We're left with liters. How many liters of barium chloride would you need? 0.300 liters. Anybody else agree with that?
Yeah.
Okay, you got awfully quiet there. What But I promise, it's really not that different when you think about it. It's just instead of using molar mass, now we're just using molarity. So again, it's literally just one more tool in your little chemistry tool belt. So, right, you've got to know which tool to pull out. Oh, if it's mass, I pull out molar mass. If it's gas, I pull out molar volume. If it's solution, I pull out molarity. It's just, that's all there is to it. It's one of those three. Okay, your turn. Try this one. What volume in milliliters of 0.25 molar HBr is needed to react with 225 milliliters of 0.350 molar Li2S? So write down what you know. Again, if you want to, you can go and you can put, question mark milliliters, 0.250 molar. 225 milliliters, 0.350 molar. I don't know. It's your choice, but something like that. So you kind of know where you're starting from and where you're going. And then just break it down step by step. So we have, stupid thing, 225 milliliters of 0.350 molar this, question mark milliliters of 0.250 molar this. So, start with the one I know both pieces of. That's the Li2S. So, 225 milliliters. How do you name Li2S, by the way? Lithium sulfide. Good. I'm going to turn my milliliters into liters. Then I'll show you a shortcut here in a second for that. And then liters on bottom. So, 0.350 moles lithium sulfide per liter. And for every 1 lithium sulfide, I need 2 HBRs. So 1 mole lithium sulfide, 2 moles HBr. But I don't want moles HBr, I want volume. So I'm going to use molarity again. So 0.250 moles HBr is a liter. And then once again, 1 milliliter is 10 to the negative third liters. What'd you get? You said 350? 630, not even close. How many sig figs is it? 3. So I'll put a decimal point there. Okay, now one little shortcut you can do. How many milliliters are in a liter? Do you know? 1,000. So one little way you can do sometimes that helps is you could say 225 milliliters. 0.350 moles per liter. 0.350 moles Li2S per liter. But liter is the same as 1,000 milliliters. That's the same as a liter. That saves you that little inversion step along the way of turning the milliliters into liters first. Are you with me? Then I say, 1 Li2S for 2 HBr. All right, let's do it real quick, I guess. That was too quick. And then I want to go, back to milliliters. So 0.250 moles HBr per liter, but I don't really want, I really want milliliters, so I'm going to do milliliters again. That's the same thing as 1,000 milliliters. So I'm just saying, as an option, if you want to do that, you don't have to. You can totally do the 2 steps and convert liters to milliliters if that confuses you. This is an option. Okay, let's do one more of these, then we'll have a few minutes to finish up just a little bit of theory stuff. So let's try one more. How many grams now? Grams of, what's that stuff called? Copper 2 phosphate, thank you. Copper 2 phosphate will be produced from the reaction of 375 milliliters of 1.50 molar H3PO4, which is called phosphoric acid, which you don't know that yet, with excess copper 2 hydroxide. So write down what you know, write down what you don't know, figure out a path to get there using the tools in your tool belt. problem says, how many grams of copper 2 phosphate? I'm going to put question mark grams. If I start with 375 milliliters of 1.50 molar. Okay? So, what do I start with? Well, the one I know, 375 milliliters. And it's 1.50 moles per liter. Or I can say 1.50 moles H3PO4 per 1,000 milliliters. Use my little shortcut. Or you can turn milliliters to liters, then do a liter on the bottom. Your choice. Doesn't matter. Then for every 2 of these, I make 1 of these, right? So for every 2 moles of H3PO4, I make 1 mole of Cu3 parenthesis PO4 parenthesis 2. Now I have moles. I don't want moles. I want what? Grams. What do I do? Molar mass. Butchered molar mass. So what's the molar mass of that stuff? 380 point. Now I'm hearing different numbers. What is it? 380.59. 380.59 grams per mole of copper 2 phosphate. Okay, and you punch it all in. Looks like 3 sig figs. So what is it? 107? Is that what you got? Okay. So we use molarity, mole to mole ratio, and molar mass, right? So again, you can mix and match them however you want. You just got to know when to use which tool. If you got a mass, use molar mass. If you got a solution, use molarity. If you got a gas, use molar volume. Okay, mix them all up. Okay, well, the last couple things, I got 10 minutes here. I'll wrap this up. Whatever I don't quite get to was all just theory stuff anyway, so you can just read it. It's not like any calculations here. But just real quickly, though, I'm going to go with 2 things. Ways of classifying solutions and some unique little properties of solutions. So first off, ways of classifying solution based off their properties. So you already know about things like polarity, about being polar or non-polar. But there's also a thing here with the size of the particles that are actually dissolved up in a solution. So a solution, we said, is basically a heterogeneous mixture, right? I'm sorry, homogeneous mixture, where it's uniform all the way throughout, top to bottom, right? So you can't see through it. It looks clear all the way through, all that kind of good stuff. Well, there are also 2 other kinds of solutions you should be familiar with. One is called a colloidal dispersion, and that we'll see is things like milk, fog, smoke, things like that. Then there's one called an actual suspension, and this is this one we'll see is a lot of it's like a lot of medicines that'll always say on the bottle, shake well before use, because they have much bigger particles. We'll see. So solutions, colloids, and then suspensions. So just real quickly, a solution, you already know that one. It's got little teeny tiny particles. They're all dissolved. They're spread evenly throughout, made a homogeneous mixture. And I'm going to fly through this because you can always read this later, fill in your notes. Again, you can't visually see any little floaties, right? Right? It looks clear, right? Salt water. It looks clear all the way through, right? You can't see anything. Okay. Now a colloid is similar, but its solute are a little bigger than the ones in a pure solution. So it is still homogeneous. It won't settle out or anything like that. But the particles are big enough you can actually begin to see some light being filtered through it. So this again is things like smoke, dust, fog, things like that. It is still a suspension. It is still spread around evenly, but the particles are big enough, and the light goes through fog, it kind of scatters. You can see that, right? Or through smoke, right? It kind of scatters through it. Okay, whipped cream, shaving cream, mayonnaise, all these things are actually homogeneous mixtures, but the particles are big enough. They're not pure solutions. They're actually called colloids. And then even bigger particles in a solution, these make what are called suspensions. These are basically heterogeneous now at this point, because now the particles in solution are so big they'll actually settle out into the bottom of your bottle or whatever. So, like I said, various kinds of medications I mentioned before. Remember it says shake well. That's why, because their particles are all settled out to the bottom because they're so big. So small particles, solutions, a little bigger, colloids, bigger particles will actually settle. Those are called suspensions. Okay. And there's a little table if you want to write that down. 8.13 has a nice little summary. Table 8.13. Okay. So last thing to talk about are these things called colligative properties. Now, these are a very interesting class of properties. They're kind of cool because these are properties that you can change in a solution by adding in a solute. But the thing is, it doesn't matter what solute you add. All that matters is how much of the solute you add. So, for example, the two most famous are, let me jump down here, are freezing point depression and boiling point elevation. So you've all heard of these, or you've all at least like seen them in action. So let's say, for example, you live somewhere where it's cold in the winter, the roads get all icy and covered in snow. What do they do on the roads? Well, they go out on the roads and they sprinkle salt all over the roads. Well, why do they put salt on the roads? Because of this thing called freezing point depression. Because water will normally freeze at 0 degrees Celsius. But if I add a solute into it, like salt, sodium chloride, or sugar, or whatever it is, and it dissolves, it will actually lower the freezing point. So now the water then will freeze at, let's say maybe it's -5 or -10. So it keeps the water on the roads then fluid longer instead of freezing to a big sheet of ice. So that's called freezing point depression. Or you do this like let's say you're at home making homemade ice cream, and you have the big tub, you have all the ice around it, and what do? Well, you add lots of salt onto the ice, right? You've done that before? Maybe not. I'm sorry if you haven't. Homemade ice cream is the best thing ever. So you take the ice, you add the salt all over it. Well, why are they doing that? Well, we're trying to actually lower the freezing point of the ice. So now the ice maker is not freezing at 0. Now it's freezing at -5 or -10. It's actually freezing it colder in that sense. Well, the opposite of that is boiling points get higher when you put in salt into them. So let's say you're at home. Then when you're at home, you want to boil some water, for I don't know, make pasta or whatever. We add in some salt into the water. That'll help the flavor, but it will actually also raise the boiling point. So now the water on your stove is not boiling at 100 degrees Celsius. Now it's boiling at 101 or 105 or 110. So your food, whatever, will actually cook faster because it's cooking hotter. So it's the same thing. So your freezing point of your salt, whatever it is, goes down, and the boiling point goes up. But the unique thing, again, about this is it does not depend what you use, what the solute is. All that matters is how many solute particles are there. So you could put salt on the roads, or you could put sugar on the roads, or you could go outside. You can pee on the roads. It doesn't matter what you put on the ice. I mean, anything you put on the ice, or in your water at home, right? You put salt in there, it'll boil hotter. You put sugar, or you can put Coke or Kool-Aid, or anything you want in there. Any kind of solute that actually dissolves, it'll make it go higher. What matters is how many particles are you getting out when it dissolves. So that's the difference. So, for example, let me look at one here. Now, so for every 1 mole of particles that you put in a kilogram of water, it's going to lower the freezing point by 1.86 degrees. And it's going to raise the boiling point by 0.52 degrees. So if you have a kilogram of water and you want to lower the freezing point, let's say, I don't know, twice that, 3.72, well, you'd have to add in 2 moles of whatever the solute is. Or if you want to raise the boiling point, let's say twice that, 1 degree, we have to add in 2 moles of particles. Well, again, it's not the whole mole, it's just the moles of particles. So for example, like I said, on roads when they're salty, icy, they salt them down, and they normally use calcium chloride. Why calcium chloride? Well, it's nice because for every 1 mole of calcium chloride, when it hits the water and actually breaks up, you actually get out 3 particles, right? You get out a calcium and 2 chlorides. See that? Right? 1 calcium, the water is going to dissolve. It's going to make a calcium, 2 plus, and 2 chlorides. So you're actually getting 3 times the bang for your buck in that kind of sense. Let's say, for example, instead they use sodium chloride, right? You're only going to get out 2 particles for every mole, right? Does that make sense? So for every 1 mole of NaCl, I would get out 1 mole of sodium ions and 1 mole of chloride ions. So I would get out 2 particles for every mole I sprinkled on the road. So it's not as effective as calcium chloride. You put down 1 mole, you get out 3 moles of particles. So it's more effective. Does that kind of make sense? So yeah, so again, all that matters is what the particles, not the one, I'm talking about they are, how many they are. Again, they could be sodium, calcium, sugar, doesn't matter what they are. Kool-Aid, I mean, anything you want to sprinkle out there actually work on the road. I mean, literally, you go outside on your road, you can sprinkle Kool-Aid packets on the road. It won't matter. It'll still melt the ice. But the question is, though, the Kool-Aid is making 1 particle or 2 particles or 3 particles, right? The more particles it makes, the more effective it is. Okay, I got 1 minute here, so yes, I want to kind of finish all this. Like I said, just go back and just read the last few PowerPoint slides. It's all just written there anyway. So electrolytes, we're going to mention. Okay. Last thing I want to briefly touch on is this thing called osmosis. This is really important, especially like in your bodies, because your kidneys, for example, are all based around osmosis. Dialysis is all based around osmosis. We see sometimes like at camping stores, they have like reverse osmosis filtered water, or reverse osmosis filters, for camping, for creeks and things like that. So osmosis is basically, it's the flow of the solvent, which is normally then is the smallest particle, going from the less concentrated solution to a more concentrated solution. And what has to happen then, it has to pass through what's called a semi-permeable membrane. So an example of a classic semi-permeable membrane is a cell wall. Your body is full of cells, and all of the walls of those cells are basically semi-permeable membranes. So they do allow small little particles through the wall, but the big stuff can't pass through, in and out. So small things like water, a solvent, can pass in and out of a cell wall, but the big stuff, your nutrients and things like that, can't pass through. So osmosis is always trying to make the concentrations inside and outside the same. So what's happening then is the solvent is flowing from the less concentrated, the more dilute one, into the more concentrated. Okay, so it's trying to make the one that's less concentrated more concentrated, and the one that's more concentrated less concentrated. So I'll draw a real quick picture, and then we'll be done, because we're over time. But that's okay, because I have you next anyway. So I'll take a quick second. So let's say, for example, I have a solution with a little membrane in the middle. Gentlemen, just 1 second, please. This side over here, let's say, is 1 molar. Okay, so it's less concentrated. This side over here, let's say, is 10 molar. Okay, all right, okay? So they're not equal, right? Well, what happens? Well, the water is going to flow from the less concentrated side to the more concentrated side. So the water is going to go like this through the membrane. And what's trying to do is again, we know if you add more water in a solution, it's going to dilute it and make it less concentrated. But if you pull water out of this solution, it's going to make it more concentrated. So its goal is to try to make them both the same. It's trying to raise this concentration and lower this concentration until they're both, let's say, what would it be? I don't know, 5.5 molar, right in the middle. Does that make sense? So that's always the goal with osmosis. I don't have time, but I encourage you, though, to look over this little bit here, though, with blood cells, especially is important, because blood cells is really important. Like when you give somebody, let's say, like an IV solution, you have to make sure then whatever solution of the IV is you're injecting into their body is the same concentration as the concentration of the solution inside the blood cells. Else the solution in the blood cell will either rush out of the blood cell, make it shrink and die, or to rush into the blood cell, make it swell up and explode. So again, it has to be the same concentration outside the cell as inside the cell. So there's a whole little slide about those different things called normal hemolysis coronation. Okay, well, that is it. So we'll see you in lab here in about 10 minutes. I'll give you a few extra minutes as we're getting out a few minutes late. And then we'll have our exam. Don't forget next class on Thursday. So make sure you bring a little Scantron, a little scientific calculator. I'll see you in a few minutes.